Welcome everyone to the next edition of Mython Times, both online and those who came in person to Karlín. I'm really happy to see so many people here. One small thing for the beginning. Today, we have a dedicated recording crew over there. They are mainly going to be focusing on stage, but they might ask you a question about how you like the event. If you don't feel like it, feel free, to say so. And yeah, nothing is going to happen. One more bit of organizational stuff. The talk is going to be approximately 45 minutes long. And I wanted to ask you to keep the questions for the end. People who are online will be able to unmute themselves. And for those who are in person, I will hand you the microphone. And now I have the great pleasure of introducing Karel Minařík. Karel Minařík is a software developer who focuses on system architectures, web APIs, interactive applications, and data visualization. Sorry. And for almost a decade, he has been working at Elastic, writing both Ruby and Go code. Until the last year, he has been helping with the digital transformation in Czech Republic as part of the team Česko Digital. And right now, he switched his focus to natural language processing and semantic search and machine learning, which is the topic of today's talk. So the floor is yours, Karel.
Yeah, right. Thank you so much. It was a great interaction. Thank you, Tonda. So yeah, let's start here. Actually, there's zero slide. All this time I was thinking that embeddings and vectors are complicated, but as it happens, like audio video is much more complicated. So we spend like 15, 20 minutes setting up this stuff. So let's dive in. I have about 65 slides, but don't worry, we're going to make it. I might go fast at times. So without further ado, the most important thing, this talk is a Jupyter notebook. So if you want, you can download it, run it in your environment on your own notebook. Everything is, code based. I'm not going to run it interactively. Some of these operations take some time, but you can do that. It was a great introduction by Tonda, so you know me. Again, my name is Karel Minařík. That's my website. You can load it up. There's everything, including my email, if you want to, follow up with a conversation later. So, semantic search. What is semantic search? It's similar asking, how does a watch work? I don't know if you've seen this movie, but sometimes the important thing is to keep an eye on the time. So you might say, I don't care about how a watch works if I can keep the eye on the time, right? But what if something happens? What if something's broken? Something's off? Then it actually is beneficial to understand how does a watch work. So in this talk, I would kind of like to explain the basics, the fundamentals of what is semantic search and how does it work. And the best way how I imagine I can do that is to actually contrast it with something we might call traditional or lexical search. And stretching this metaphor of how does a watch work a little bit, we might say that the traditional lexical search is something like a mechanical watch. And semantic search is something like a quartz watch or a digital watch or a smartwatch. It's really much more complicated and really less transparent as opposed to a mechanical watch, which almost nobody uses. We use phones to keep an eye on the time, but you can actually see the mechanism. And that's a really big pro of the traditional search because it's really transparent. You can look inside. For instance, even Elasticsearch, when you run a query, can tell you the explain part of the request, like why did it score a particular document in a particular way, right? But it works on the fundamental level of language, words, terms, frequencies, right? TF-IDF, the term frequency and inverse document frequency, BM25. Sorry, there's a lot of math involved, actually, counting all these frequencies, keeping track of these statistics. But fundamentally, it's about words. Like in the dictionary, therefore, lexical search. The engine does a lot of transformation before it actually feeds your words into the index. Like, might be really something simple, like lowercasing the string, because people usually, type their queries in lowercase. but also might be something like stemming or lemmatization, like more significant transformation. The semantic search, or vector search, as it's called sometimes these days, works completely differently. It works with text embeddings and their similarity. And we'll really go a little bit deeper on the next slides into these topics. But the important thing to keep in mind is that fundamentally, semantic search is concerned with the meaning, whatever that means for this moment. And the lexical search is concerned with the words, with the text itself. That presents at least one of the problems for the traditional lexical search, and that's called vocabulary mismatch problem. If you know what you're searching for, then you're going to find it. These, old algorithms, even TF-IDF or BM25, are really super effective, even when you run current benchmarks with them. But you need to know what you search for, the exact word or the term. If you don't, so slightly less chance or even no chance of finding that. That problem is kind of missing from the semantic perspective, and we'll see an example for that. Another thing I want to highlight is that in this talk, we are going to be concerned with text, and our data will be Wikipedia, so it's strictly text. But there's no limitation whatsoever to use semantic search for other modalities, as is the technical term. So images, sounds, other type of content, which you can transform to embeddings. And that's our next topic. We need to kind of clarify what it is. In its core, embeddings are basic mechanism for natural language processing, right? Every application of NLP, be it sentiment analysis, machine translation, which is actually the origin of this idea, or the large language models, are based on text embeddings. Physically speaking, let's say, these are numerical representation of text content, in case of text, obviously. That text content might be small or large, might be individual words or sentences or phrases. And since it is a numerical representation, we can do math with those numbers. And that's the fundamental mechanism how it actually works. More conceptually speaking, we can consider embeddings to be something like a GPS coordinates for meaning. If you think about it, a GPS is a pretty useful system. There is a list of numbers, just 2 numbers, latitude and longitude, and that pinpoints exactly this room on the planet. And it's really easy to, for instance, distance the measure from this room to your home, if you know the GPS coordinates for your home. That is, I find, a really good mental representation of what's going on when we actually use embeddings to compute similarity and to use that for searching. The difference is that GPS is 2 numbers and the embeddings is usually hundreds or thousands of numbers, and that presents a couple of problems. I'll again demonstrate them. And the last thing, sometimes people think that these embeddings are something like tokenization. That's not true. It's not a super smart algorithm which magically understands human language. It's a pre-trained model in a really similar spirit to ChatGPT, GPT-4, Claude, and other large language models. It's pre-trained on a really huge corpus of text, and by this mechanism, it can kind of infer the meaning behind these words. There are links, I will mention them, to save time later on. I really encourage you to click through them. These are really good resources in general. So what embeddings then enable us to do is kind of have a representation of our world. In the words of Ilya Sutskever from OpenAI, they understand the projection of the world behind the words. So for instance, this is a project from TensorFlow from Google. It uses a really small data set. Word2Vec is like super old data set, just 10,000 items. But see what happens here. If we query the embeddings for this dataset for Python, you can immediately see that it kind of slices through the semantic space in a specific way. The bottom half is mostly related to Monty Python Flying Circus, right? That's the origin of the Python programming language name. So you have the comedy and Cleese and Chapman and circus and all these things. But in a different direction, you have programming and Perl and JavaScript and all these concepts and words related to programming. And there's nothing magical to it, although it looks like that. Because this is a projection which the model can learn from, a lot of texts, like terabytes or petabytes of text. So with this picture in mind, let's move further and let's try to understand what actually is semantic similarity, how you can actually say this word or the concept behind that word is more similar to this than this. It's easy. It's just dot pro. I mean, no, I can't understand not formulas, by the way, but I can understand Python. So on the next slide, I have a really nice representation of what's happening. But let's just, recap really fast what we've learned. Embeddings are lists of numbers. There's nothing magical to it. GPS is 2 numbers, and the vectors are just more numbers, like hundreds or thousands. With math, we can calculate distances, Euclidean distance, dot product, or cosine similarity, which is usually the most precise, slower than the other ones, but it's a good trade-off. We'll again encounter this trade-off between precision and performance in the talk many times. So we can actually set up 3 vectors, 6, 7, 8, 9, 2, 10. And if people are here from the mathematics department, I'm sorry, if there is an error, please tell me afterwards. And we can actually stick them into a matrix, all of them, compute the similarity by using the scikit-learn package. So we don't really understand how the watch works. We use Lego pieces and just put them together. But at least we can compute the distances between these vectors. And that's what's happening here. Because as you can see, this is much more similar than this, right? And that's the same thing in the vector representation. You can see that the distance is something like 1 degree, as opposed to this, which is something like 30 degrees. The problem is that this is a 2-dimensional representation, and it's pretty easy for us as humans to understand. We can add 1 dimension possibly, like 3D, so we have it in space, and maybe even 4th, like time, and have it animated. But that's it. That's our limit. We will never be able to, imagine effectively anything with more dimensions. And now the model we are going to use has more than 700 dimensions, right? But the thing is that the math behind a computation like this works in the same way for a 2-dimensional matrix and for many more hundreds of dimensions. I've said that we need to actually generate these embeddings, right? So the model we use is this multilingual E5 base. It's from Microsoft, and Infloat is one of the primary authors of the model. It's on Hugging Face. There are 3 versions: small, base, and large. This is like the middle ground. It is a really nice API. So you just import the package, initialize the model, and then run the encode method for a word, sentence, or something like that. So an embedding, vector embedding for word clock, it's just a list of numbers, and it's 768 numbers. There are methods you can use for this, right? Hugging Face has this space, which is really useful. It's a leaderboard for all sorts of different models. The trouble is obvious too, I guess. Like 97% of them is based on English. there is one tab for Polish, and the E5 multilingual kind of wins that thing. It's a synthetic benchmark. I think that most of these benchmarks are basically scam, but it tells you something, right? So you can choose different ones, and the space is constantly. So what I'm saying right now is maybe even obsolete. So for instance, there is an E5 Mistral model as of, I guess, last week or the next week before, which is kind of an amalgamation of E5 and the Mistral large language model from Mistral AI. There's a new model from last week, and that will be next week. Don't worry, right? But we're gonna stick with this one. It's pretty useful. So let's kind of observe how it works when we try to do something like we did with the vectors, but now with words and their embeddings. So this particular model has a different prefix for query and for the data you encode, query and passage. This is particular to this model. Every model is different in this way. We have 5 words: cat, mouse, house, kitten, and clock. We just run encode on all of them with a passage prefix, and we stick them into a pandas data frame. Sorry, so it looks like this. Not terribly useful, right? So what if we try to compute the cosine similarity between these numbers? Now we have the numerical representation, not words in any way. Again, using the cosine similarity from the scikit-learn. You see there are 2 versions, original and normalized. This is kind of tricky. I've run into this when I was preparing the talk, and I decided to kind of transparently show you everything, so you know how the watch works, right? We just compute the scores and display them over there as the first table. You notice that the order kind of makes sense from the most relevant to the least relevant. So cat, kitten, mouse, house, clock. But you also notice that the difference between the scores, the similarities, is negligible. It's like really, really small, and it's almost useless. So as it happens, this particular model is not really concerned with scoring like this, with the exact values. The training was focused on proper order, let's say, of the related items. But in order to kind of understand more, because I don't know about you, but I can see a difference between 0.79 and 89. It's like really hard to understand what's going on. We can include a scalar again from scikit-learn and just kind of crop these values. So this becomes 0 and this becomes 1. And in the bottom table, you can actually see that the model really understands well that a cat is similar to kitten. Kitten is a small cat, right? So they're pretty similar. Both are kind of similar to the mouse, because possibly the model saw a lot of text in English where cat catches mouse, etc., etc. But there's not so many relations between cat and house and clock. So that's fundamentally what's going to happen later when we run a computation like this inside Elasticsearch. This is, let's say, a brute force approach, right? We're just iterating over all these words in the data frame and just computing the similarity. This is actually not what happens in Elasticsearch or pgvector or VV8 or the other vector databases. There are a lot of optimizations actually happening for that. All right, so let's move on, because this was the basic mechanism, but we want to actually use Elasticsearch for all this, because it's a pretty capable vector database. Not many people do that, and I think it is. So what is the time? We have to keep the eye on the time. I think we're good. Our workflow will be basically 5 steps. we will need to kind of pre-process the data, and it might sound boring and insignificant. Funnily enough, is usually the most important part of the whole process. We will need to generate embeddings and do that efficiently. I will explain a couple of tricks you might do to make it run faster, to save time or money. We have to index these embeddings, search the data, and it would make sense to kind of evaluate the search quality, to not just randomly look at a couple of results and say, hey, this is better. I feel like it's better. The outcome should be something like this, like a web application. It's online. You'll see the link later on, where we can compare semantic and lexical search. Now you immediately see that it appears like the semantic search understands slightly better, and you can also in this version use different models. Not in this talk. In this talk we just use this one. We will use the Wikipedia dataset, as I said before. Luckily, Wikimedia has put all the pages neatly organized on Hugging Face. So this is a split for the Czech version from November last year. The dataset is pretty simple. It's just ID, URL, title, and text. The text is plain text. There is no structure, no markup, which Wikipedia uses. And the title and the text. In the search, and I will emphasize it along the way, that we will search just the text. We will completely ignore the titles for reasons I'm going to tell later. So this pre-processing the data, I mean basically splitting the text into semantic units, which makes sense. If your text is not text-based, if it's PDFs or images or something else, you obviously need to transform that into embeddings in another way. But for us, we're working with text, and we need to make a decision what's like the most reasonable semantic unit for us. Is it like a chapter in Wikipedia or a paragraph, single sentence? It's hard to make this decision. But ultimately, we're limited by the model context window. And different models have different context windows. You very probably heard that people do experiment with models which have like tens of thousands of token line windows. This one has 500, which for Czech would translate to something like 200 words or something, or less maybe. So not that big. If we just display the text for the first page, which is about astronomy, this is how it looks like. It's plain text. There is some form of structure. At least the paragraphs are separated by 2 lines. So let's say we, use that as kind of our basic semantic unit. Because if you think about it, especially in a text like Wikipedia, a paragraph in a text, that's a coherent thought. Usually, people don't change the topic in the middle of the paragraph. Usually, right? So let's do that. Let's just split it into paragraphs. We could use this, but notice what happens. Some of these paragraphs are really short. Some of them are really long. Some of them might not even fit into our context window. So the rest would be cut. There would be gaps in the understanding, and we would have no way to actually know what's going to happen, right? So we could do different things, but let's say we use a smart tokenizer from the Morphodata package from UFAL, and we split the text into sentences. So then we actually do split into paragraphs and into sentences. So that's what you can see on the right-hand side. So no matter how the paragraph is long, we have the individual sentences. And notice something which I want to point out, and why I didn't use, for instance, a regex with a dot or something. This particular tokenizer for sentences does understand something like, před naším letopočtem, or it understands check dates. That's pretty important, because otherwise we wouldn't get sentences but junk. And let's now split every page into chunks, respecting this context window. This is kind of a little bit of boilerplate. We're putting the model on the fastest device we have in the particular environment. Again, this is the model we're using, and the maximum is suddenly less because we also subtracted the prefix token. Oh, sorry, the tokens for prefix. So one, and I need to go a bit faster, so the code you can read later on at home. This happens. And you can notice that all the paragraphs are actually kind of the same length, and they kind of split on, let's say, semantic boundaries. For this particular page, there are other pages, but for this particular page, which is representative for Wikipedia, it works. Mind you, it always makes sense to kind of inspect your data and see if it's not completely off. So for instance, I was curious if there are some chunks over a limit. Yes, they are, like 8%. Inside the illustrations, it's junk text again, text without dots, tables, bullshit data. That usually happens. Data is junk, and the most important part is cleaning up the data. It's like always. But the number is kind of good. The average number of chunks is 6 per page. Maximum is 83. That's okay. We can work with that. So since we now have the chunks, let's generate the embeddings. This part is really computationally expensive. This part is where, if you have a GPU, it makes sense to use it. And the performance really depends on the hardware, but also on, let's say, hyperparameters for our code, the batch size usually. We have a couple of wrappers to measure the durations for individual functions and then aggregating statistics. Again, we're not going to go through the code line by line. And we do have like a generic wrapper where we pass the data set and the function, and we pass that function inside the dataset map function to really perform the embeddings in 3 different ways. So let's have a look at the first way. This is the most easy and simple way how to do that, like for humans. Let's just iterate over all the chunks, for a page. Then let's just iterate over each chunk in those chunks, generate the encodings, accumulate, append, return. All right, but the throughput, as you can see, is like 2.5 pages per second, and the entire data set would take about 2 days to compute, which either you don't want to wait that long, or you don't want to pay so much money for that, right? We can be smart because we know that especially GPUs, they love large batches of stuff to compute. Take the biggest batch you can without overloading the system, running out of memory. So we can take all the chunks for a page, push it to the middle, and generate everything at once. Cool. We have improved the output twice. It's now 5 pages per second, but it's still 1 day on this hardware. It's a full MacBook M3. So it would be slightly faster on a real GPU, but not that much. I'll show you a chart in a minute. So I was thinking, can I make it even more faster? So what if I just put some amounts of data to the GPU? What if I shovel like everything I can? So I will completely ignore the pages. I will just flatten everything, put as much as I can. That's the encode batch size 1000 into that. And then, unfortunately, I have to reassemble everything again, keeping track of the index and, not mess the chunks for different pages. But we improved the output 4 times. And even on this poor notebook, the time is 6 hours. So that's doable. I actually did experiments because you see I'm performance junkie. So I run the 4090 and NVIDIA A100. And Meg is here, 2 meg. It's like 20 is the upper limit for the fastest version. That's the last one. The RTX 4090 is kind of okayish, but obviously here we have, the biggest throughput is like at 90, sorry, or something. And the important thing is that this is the first sequential thing, and you notice this almost as fast as this notebook. It just, you really are not using that hardware. So keep that in mind. Obviously, you cannot overload the memory, but run it with as much stuff as you can on the card. Or you can load the dataset, which I did, and put on a Hugging Face. So this is what we're going to use now. So we have the data. We have to index the data. Performance windows number 1 and 2. We're going to set up indexing, and it's not really that important. What is important is index mappings, and I want to emphasize at least 2 things here. So we need to tell Elasticsearch how many dimensions or dims we're going to use. We can query that dynamically from the model. I encourage you to do this. Every field in Elasticsearch can have a special meta field, and you can put anything you want in there. Put the model ID in there, because if you don't, you won't ever remember what you did, what kind of model it was. I don't know. Maybe you can guess based on the dimension, but I don't know. And this is the really important part. You exclude the embeddings from the source. And if, I don't know how much fun you are with Elasticsearch, but Elasticsearch stores everything you send to it on disk. And these embeddings are super large, so it's tens of gigabytes of data, which you're never going to use, because you will perhaps never ask Elasticsearch, hey, return me embeddings for a word or a sentence. Doesn't make any sense. You just index them and use them for computing cost and similarity. So right, we have that. We create the index with a simple twist. Notice I'm doing that even for simple demonstration like this. We will set up an alias. That's pretty cool, because then we can kind of swap the index under this alias anytime we want, and we are not going to change Wikipedia search sample in our application ever. And here comes the first performance thing. This is particular to the Hugging Face datasets. So if you're not using them, it doesn't apply to you, but the lesson does. I was concerned that the throughput was really, really slow. I didn't know why. And then a colleague asked me, did you run it like raw, like just iterating over the dataset? And it was that slow. It's 20 seconds per one loop of the iteration here, just doing nothing. If it's with format NumPy, then the package very efficiently loads everything from the disk, doesn't convert to Python lists, Python dictionaries, which is the time you pay the price. And also with the ITER 1000, you again batch things. If there's one topic for this talk, it's like watches and batches. Because see, it's 3 seconds from 20. So when you index in Elasticsearch, even me, and I was working at Elastic, and it didn't occur to me that I should really measure the raw iteration. That should be fast, right? No, it's not. There which isn't fast, and there's actually NumPy serialization into JSON. Check these numbers. So the first line is like regular JSON dumps, the built-in JSON package in Python. It's 29 microseconds. Like, that's nothing, right? But if you use an optimized Python package like OR.json, it's 2 microseconds. It's 10 times less. And if you do this operation millions or hundreds of millions times, obviously you pay the price. So with this in mind, we set up a special serializer for Elasticsearch. It's really easy. This is all you have to do. Like copy paste this code, it's going to work. And we will create a generator for batches. So we can basically, for each page, have this part, which has an array of a chunk, embedding, chunk, embedding, chunk, embedding, right? It means, again, on the notebook, you're getting something like 3,000 docs per second, could be like 10 times more on proper hardware. And we can do another optimization. And I don't have time to dive into this, but we can talk about it later. Elasticsearch index is composed from shards, right? You possibly know that. And each shard is composed from segments. There's a lot of segments for this one shard, And these segments are really small. It's like a couple of megabytes sometimes. You can read this at home, but you can actually force merge everything, like vacuum or other operations, into a single segment, which is much smaller than the original index, A. And then the operations for computing cost and similarity are much faster. And I mean, it's a dimensional difference. Before I did this, the queries took like 1 second, 1.5 seconds. After like 15 milliseconds, 100 milliseconds. A really big difference. Okay, data is indexed. Let's search it with the alias, with the device. For the traditional lexical search, remember the beginning of the talk, we are going to use the match query, and it's wrapped in this listed part because we index everything. I didn't highlight that in the mapping as one document page, and inside the document we have something Elasticsearch calls a nested document, which might be like 10,000 small documents, right? And we use the match query against the chunk, which is the text, analyze with the check analyzer, again, something I didn't point it out. We're getting like similar hits, like the matches, and we sort by score, obviously. For semantic search, again, we make sure that we prefix the query with query in order it to work. And then we use this KNN query, which is the latest addition to Elasticsearch. Before it was a top level field in the request definition. Right now it's a regular query. It's nearest neighbor search. So basically what we saw, where we encode the query and again return 500 hits. Some helper methods for searching and displaying the results. And let's see what happens when we search co je to staroměstský orloj. What is the Prague astronomical clock? As you can see, the lexical search is really confused about this quite simple query. Mind you, it doesn't search in titles, and there's obviously a page on Wikipedia which is called Staroměstský orloj, exactly that thing. That will work much better, or not that much better, somewhat better, but all these other results are really useless. I mean, I didn't know that there is a Chmelový orloj, for instance, or I didn't know that there is an Nábřeží Maxi Psa Fíka. For non-Czech audience, it's a Czech cartoon for kids, Maxi Pes Fík. Okay, but there is a logic to this, but these results are mostly useless. And I don't think that in the first 15 results there is that page which we would like to see, and that is called Staroměstský orloj. So what happens when we do the same query with the semantic search, with the base model? So first position, orloj. It's from Italian, that's the orologio. That's the thing we're kind of interested in. On the second position is this page, Prague astronomical clock, Staroměstský orloj. And then a couple of weird results, maybe again Nábřeží Maxi Psa Fíka, I don't know. But at least we have Mr. Hanush, who's the creator of the clock, or he's not. I did this talk, so I had to learn everything about Prague astronomical clock, But mostly these results are like reasonable and relevant, right? Let's make it really hard for the lexical search right now, and let's demonstrate vocabulary mismatch. What if we phrase the query like velké staré hodiny pro turisty v Praze? for a big old clock for tourists in Prague. There's nothing about Staroměstské náměstí, Old Town Square, the Orologio, nothing like that. So the lexical search is completely, confused. There's a Croatian, something for tourists. There's a clock tower. Okay, there's a tourist. Not really. Basically, no. So if we do this with a semantic search, it is kind of confused as well. So there is this like public lighting in Prague or something, and the kind of Orloj is better. I don't know why. There's a couple of weird things, but at least on the 5th place we have Staroměstský Orloj, the page we want, and then we have mostly, I would say, related results. You can check at home, but it appeared to me that at least this thing is related to Prague astronomical clock in some way. You can check this application at home. There's another, potentially hard query for the lexical search. Které město v České republice má nejvíce obyvatel? Which city in the Czech Republic has the most inhabitants? I mean, we found in Canada, it's not really related to this, right? And hypermarket isn't. And what is this? Yes, on the 5th page, we have something like this, right? If we try the semantic search, the first hit is really this, the list of cities in Czech Republic, sorted by the inhabitants, and then the list of cities in Czech Republic, and again a list, and again a list, and a big city, geographical records in Czech Republic. You really might say that this is related. So in this way, the semantic search wins. It's not a panacea. It's not a silver bullet. Just today, I read a benchmark where BM25 actually was better in some kind of benchmark than semantic search models. But it's really useful to understand how it works and to try it with your data, because I've seen great result with my own data in my applications. Two last things. So performance when you run the inference. Obviously, running inference, like when people come to your application, you need to encode that query, they pass in. Then there are two, but I don't need to buy GPUs for them. It's really, really expensive. You actually can run efficiently these models on CPU with the Onyx runtime. It is a lot of acrobatics with Python, but ultimately we have a method called encode for the ST, like sentence transformer model, and the OP, like the optimized or optimal model. And notice the difference. For the regular model on CPU, it's like 18 milliseconds versus 4. One fun thing I collaborated on this with Tunda, right, is that I was wondering, are these numbers actually the same? It's cool that it's fast, but it also has to be kind of precise, in a way. They aren't up to a certain limit, right? So it's again about the trade-off. Everything is a trade-off. So now we're trading speed for precision. In the notebook, there is evaluation of results, like results from Elasticsearch between the normal, let's say, sentence transformer model and the optimal model. The results are the same. It's like 99.8, match. So it really doesn't matter. And with this in mind, if you do this, I really urge you to do some kind of search quality evaluation. It's really easy, especially with Elasticsearch, because it has a ranking evaluation API. In our case, we're going to compare the lexical and semantic search, and it has all the standardized metrics like precision and recall, mean reciprocal rank, or the discounted cumulative gain. We're gonna use. The best part is that you need to come up with an evaluation data set. Nobody will do this for you. You need to understand your data. You need to come up with a list of results which are relevant, more vectors. So here we're starting from 5 for the Staroměstský Orloj page, 4, 3, going down until we find Nábřeží Maxi Psafíka, right? We don't want that. So running the evaluation is super easy in Elasticsearch. This is the actual API call. This is the definition for the lexical type of search, and this is the definition for the semantic part of search, similar as before. So if we do some kind of, again, acrobatics with Python and Jinja, we end up with this. So for the query, Staroměstský Orloj, you can see that the lexical search is really kind of bad. It has this Orloj page on the sixth position. These results are mostly not relevant. This is relevant, but it's really down below. We're running until 30 in order to find the most relevant page. And that's perhaps why the normalized discounted cumulative gain is really low compared to the semantic one. Because as we saw that previously, what's not that great result, but on the second and third position we have relevant results. Then it's kind of mixed story, but we have this, and that's all. So I'm sorry, I'm over time, couple of minutes, but that's all. Thank you.
Now is the time for questions. There have been a couple already posted online, so maybe we can start with those until people think of some. So yeah, the first one was if, in your opinion, it is worth doing something like quantization or not at all with the embeddings.
It makes sense, yes, and it's actually the official recommendation of Elastic, I guess.
Cool. That's good to know. Yeah, the second one is the one that I already also had was, is it possible to combine the lexical search with semantic search in Elasticsearch?
It is. Actually, Elastic does sell this feature pretty heavily. So you can do that. And there's also a re-ranking feature in Elasticsearch. So you can actually do that. Kind of combine these results, like best of both worlds or something like that.
Nice. Thank you. There are two more online, then I suggest we'll go through the questions here. So okay, so another one is, can you give examples of when lexical search is more suitable than semantic search?
I'm afraid I would repeat myself and say, if you know what you're searching for, so do not be stupid and rephrase it in a better way. If your users are, for instance, advanced enough that they are familiar with the vocabulary, like, for instance, librarians are usually very effective in searching because they have a really good mental model, how these things works.
I get it, I think. Thank you. Yeah, the last one that's been posted to chat so far is, I don't know if you've encountered that, but somebody is asking, how would you deal with non-deterministic embeddings being returned? Like if they were different each time you submit them to the model, if you didn't want to use caching.
That should happen. Like
I also haven't seen that happening in the wild, but
I didn't try. But I was really confused that the numbers between the Onyx version and the standard version were different. And actually, I did find, I don't know if you saw that on Twitter, there was a guy who did run the same PyTorch code on CPU and GPU, and the numbers were different. So
we've seen that as well. So yeah, there are some questions here, right?
Thanks for the talk. I want to ask about scaling it up. So what is the largest index that you have tested? And let's say with some optimized search, not the brute force one. And could the latency be between like 50 to 100 milliseconds? Thanks.
Yes, yes. The answer to the last part is yes. It could be, and it is like try the application. It's running on Google Cloud Run. Really like not really performant thing, and Elastic Cloud is really like standard. It's perfectly normal to have like 50 milliseconds, but it has spikes. The first part of the question, scaling. So the good part about the answer is that it's as everything in Elasticsearch. It scales as everything in Elasticsearch. So you have shards, and therefore you have parallelization. Even computation, on these shards takes. I can use the threading on the system, the CPUs, etc., etc. If you have multiple machines, then you can put one shard here and the other shard there. Obviously, you double the performance, right? There is some overhead in the coordination then, but you can scale, horizontally pretty well.
Yeah, let's say. Do you have a benchmark for it? Like,
Not
I have,
really.
like, I have looking into tutorials for different services, and they usually look at like very small indexes, not very
Yeah.
small, but like not real life e-commerce level, for example. So you don't have any data.
Well, I do. I mean, no, it's not that bad. So this is 500,000, pages, right? And the search is super snappy. I can load up the application there, and if it's warmed up, like if there's enough workers, it's super fast. What I did personally in my application was something like 5 million documents, and the performance was completely fine, right? Without these tricks like the JSON optimization, I really urge you to do that. 100 is completely doable. But then again, you need to think about it. And for instance, that first merge optimization trick I did, that's super useful if you don't change the data. Because if you do, Elasticsearch will create another segment and another segment, and then you have a super large segment which will never get evicted. So, trade-offs, right?
Right. Thank you. Are there any more questions? Yeah.
Yeah, perfect. I would like to ask, like, what's the reasoning behind using the, what was it, the query and passage prefixes for that? If it because like you showed a comparison for cat, and cat is quite similar, and I would say 100%, not 89%. So if that makes sense, and if it's the kind of question and answering kind of part of that.
Well, yeah. Let me think. So, it's really particular to this E5 model, right? So, for instance, the mini LM model from sentence transformers and these others, they don't require you to do that. This one is, and they have a paper which I kind of skimmed, and I vaguely remember. Why they do it is because they use something like contrastive learning, I think it's called. Maybe Tunda has more information about the particulars, the mechanics, where you need to teach the model basically what is relevant and what is not. And you do that, and now I'm hypothesizing that you need to do that in a different way between the query and the passage. But that's my hypothesis. I guess the paper has all the details. So.
Right. Are there any other questions? Yeah.
Okay, my question is, what is the benefit of using Elasticsearch in this use case compared to other vector databases?
I have a great answer to that question, actually, because I'm already using it. And this is actually what I tell people when I'm consulting and they ask me this question, and they use Elasticsearch. I'm there because they are using Elasticsearch, and they ask me, why should we use that and not pgvector or VVet or Pinecone or guess what? And I'm telling them, listen, guys, you already have the cluster, you have everything, just use it, right? So. And honestly, there's my answer, right, to these people. But then I understand your reason behind your question. I would say that it's a pretty capable vector database, and I think that like the killer feature is really that you can very easily combine the BM25 search, like the lexical search, and the semantic search. And for instance, Vespa, another vector database, right? They sell exactly this feature because they are also able to do that. So that would be one reason. The other reason is that I trust Elasticsearch to really scale, as was this question, right? Because I know how the scaling works, and ultimately, it's all the same. It's some kind of computation on files on disk, which are loaded into memory, etc. So if I kind of can spread this across a cluster, across different physical machines, should scale. So that would be the second part of the answer.
Yes. Oh, okay. One more question. I think we have time for the one.
In your talk, you were, you were showing an example of search across documents, and this is an example everyone is showing on the internet. Like all the examples, they contain this across document search. Have you ever seen at least one article, one paper, one person? If there are some people who are doing search in document semantic search, and maybe there are some benchmarks on this, because this granularity of searching it's a different story. If we start talking about in document search, the main question is not about performance. It's about what to embed, and basically what to embed. It's the main question in this case. And
so just in order I understand well, like the corpus would be just the one single document, like pretty big one maybe, but like a single document, right? In a strange way, that's actually what happens in the talk, right? Because I have a Wikipedia page and a couple of them, right? And I split the text into these chunks, which is basically like an array. And that's actually what I'm doing. And if I'm not mistaken, fundamentally, you need to kind of split your content into these semantic units. Might be some sentences, right? And for let's say small data, not big data, sentences might work really well. So I would say the mechanism would stay the same, but that's why I try to highlight the importance of proper splitting, because that really influences what's going to happen next. Then you have the question, which model should I use, and which model is better and larger, and then you need more hardware for that, right? But it's a completely different question then. But the first question I would ask, what is a good semantic unit for me? For instance, like lawyers, maybe a paragraph is not a good unit. Or what people do, they summarize either the whole document or a first chapter and the second chapter, and they feed into the engine like a summarization. That would be pretty easy, pretty easy workflow in this case, where you would not split the, let's say, raw text of the Wikipedia page. You would kind of either split it or tell GPT-4, hey, split this for me into 5 chunks. And then you would take these chunks. People do crazy things, by the way, if I might abuse your question for mentioning that. People do sometimes things like, okay, we accepted the query from the user, right? Encoded that and we did run it against the corpus. What people do is they take the query, pass it to GPT-4 or Mistral or something, and tell it, hey, create a hypothetical document for this query. And then they take this hypothetical document, encode it, and run it as a query. Open, stuff with this. They had this Czech event last year. You can look it up. I might disappoint you. They say it's really small difference. You just forget it. Sorry.
All right. We have run out of the time, so please let's thank Karel again for the great.
Thank you for coming. My pleasure.
And again, a little bit of organizational stuff. So Mitten Times happen roughly once a month. We're gonna announce the next edition on Meetup.com. We don't have the date confirmed yet, but yeah, it's gonna happen likely in just about a month. And for those who are here in person, there's some refreshments prepared. There's beer on tap. Pizza is coming on top of what's already in the room. So everybody is welcome to stay as much as they like and talk. And yeah, thank you, Karel, again.
Thank you. Thank you all. Thank you.